Hello, my name is David Voiles and I'm a technical evangelist at Microsoft, and today I want to discuss with you a bit about Emscripten, which is a tool that allows us to transpile C or C++ code and turn into JavaScript and HTML5 so we can take some of this older legacy code or get some good reuse out of it and allow it to work inside of our modern day browsers. Now, during this talk, I want to illustrate some practical points of how this works, but also how someone may use this in the real world, and even highlight some use cases and examples of how many developers I found in the field are using this today. So to understand this, first, we've got to understand that JavaScript is standards-based and the only language that runs in all web browsers. So obviously here I'm highlighting a number of the desktop browsers, but JavaScript will play just fine inside your mobile devices too. You can run only JavaScript in browsers, but you can write in another language if it compiles to JavaScript, and that's exactly what this is about. So we can take C, C++, and perhaps some legacy code we're working on in other languages and transpile it to JavaScript. So everything compiles to LLVM bitcode, which can then be turned into JavaScript. So for those who don't know, LLVM is the low-level virtual machine, and it's a library that's used to construct, optimize, and produce intermediate and or binary machine code. It can be used for a compiler framework where you provide a front end, such as Clang, which is made popular by Apple, which is a parser and a lexer, and also a back end, which in this case we're going to be using Emscripten, and that's code that converts LLVM's representation to the actual machine code. So, practical use case, starting in 2005, Apple made extensive use of LLVM in a number of commercial systems, including their iPhone development kit, Xcode, and 3.1 of GLSL, their graphics library. So native code definitely has its perks. Let's get that very clear. So writing something in C or C++ has a huge perk, and that's performance. But so does rapid testing and sharing, right? So for example, I can transpile my code to something like JavaScript and just share a URL with you. That's very convenient. I can hop on Twitter and I can tweet a link to the project that I'm working on, which you can then use and showcase directly inside the browser. That doesn't get any easier than that. But this is nothing new. Well, at least sort of. So for example, other languages have been doing this for a while. They've all been able to transpile to JavaScript. So for example, Py.js used Python, JSIL, very popular project to take .NET, but specifically C# to JavaScript, and even Java, which Google worked with several years ago, called the GWT or Google Web Toolkit. So you may be asking, why now, right? And there's a very good reason actually. And it's because non-standardized approaches such as ActiveX, Silverlight, which Microsoft was responsible for, Flash or Owlchemy from Adobe, Pinnacle, have had limited success in the past, right? So these were third-party or proprietary tools that we were really trying to shoehorn into the web to try to get some of that native performance and things that we were looking for that native applications offered, but perhaps the web wasn't really ready for. So why now? Well, because plugins outside of HTML5 standards, that is all those things I mentioned just before, have not received the widespread adoption for both technical and non-technical reasons, which I won't get too deep into now. But fortunately, now we do have standards, right? We have HTML5, which granted is a constantly shifting and growing platform, but at least it gives us a common target to attempt to hit. So standards are not the same across the board, or in terms of adoption, I should say. So one browser may adopt a standard earlier or perhaps a bit better than another browser, but at least we are starting to get a more common ground to write code for. And besides, all of those things I mentioned before are either out or on their way out. And here's a practical use case. So no plugins for iOS devices, right? So there goes a huge part of the market you're trying to hit. Google nixes an NPAPI, so here we go. Even earlier this year, you saw from April 14th, Ars Technica had an article saying Chrome starts pushing off Java off the web by disabling plugins. And again, there are a number of reasons behind this, but I want to make it very clear that HTML5, or at least the JavaScript and web-based standards, is where the world is beginning to go. So this is great, right? You're thinking, okay, we have web, we have standards, and JavaScript is a standard, so why not compile to that? Well, here we go. How about this for an example? Gaming on the web, right? Let's see what it's like to experience, or at least what your experience is like with a typical game. Okay, that is, I go to a platform-specific store. We'll look at something like iOS store, right? The App Store, wildly popular, or something like Steam. I'd go to that store. I'd then have to log in on my device. Again, I'm explaining all this from a desktop PC, so I'd go to Steam, log in. I'd have to then go find the game, purchase the game, perhaps enter my credit card information again, then download that game, wait until the entire thing is done downloading before I can start to run it. Which is a good thing and a bad thing, right? Maybe I only want to get through that first level, but in the end, I've still got to download the content for that final boss, which I may or may not ever even experience. But the fact of the matter is, I still have to tax, my machine to download all that content. I got to tax your servers to get all of that content. I then got to install that application. Is it compatible with my device? Does it work with this operating system? Is everything up to par? And I've got to perhaps patch before I can even play it, right? We see operating systems, and it's the holidays happening right now. You see pretty often on Twitter, people are saying, hey, if you're buying a console for somebody or electronic device, go and update or patch it immediately before they open it up and get to use it on the holiday. And then I can go play the game. So quite a few steps there. With the experience on web games, I could very easily tell you, go to my website and play some of the games right now. So at my site, davevoyles.com, on the top tab there, we'll see HTML5 and JavaScript, and those are games you can just hit play, and it'll go right there immediately. A very different experience, right? Any changes, patches, updates, they'll all be applied to that one bit of web code, which will then work across, ideally, everyone's devices. So JavaScript was not always what it is today, right? So we'll discuss JavaScript then as well as JavaScript now. So then, JavaScript began as a very slow and interpreted language in the 1990s. It was created by Brandon Eich, who was working at Netscape at that time, and was building a language for Netscape Communicator, which allowed us to really have scripts and, we'll say, more dynamic pages inside of the browser instead of the static content that many of us grew up with in perhaps the early 90s. So I'm sure you're very familiar with this. Old version of Internet Explorer. Stop running the script. A script on this page is causing Internet Explorer to run slowly. If it continues to run, your computer might become unresponsive. Yeah, that's not a very good example for or experience for anybody, right? Nobody wants to go through this. So that's what the web used to be. Very slow. JavaScript just wasn't implemented correctly across the board, and we're really trying to, again, shoehorn in a lot of these third-party extensions to get people to adopt the web. But JavaScript now, we have implicit statically typed code in JavaScript, just like the competition. And the competition, again, was things like C or C++. So in this use case here, I have a very simple JavaScript function where I'm adding variables A and B. And you see I have a vertical bracket and the 0 right there. So what that's actually doing is that is telling the JavaScript compiler that I want this code to be run as an int32. Now, typically, JavaScript numeric values are going to be in double precision floating point. But here, I can actually say I want it to be this type of numeric value. And I can have int32 mathematics happening inside of the browser. So this is something called Emscripten, which is a subset of JavaScript I'll get into in just a moment. But I want you to understand some ways we can actually start to optimize our JavaScript code now. And I mentioned before Emscripten, or asm.js, that's assembly JavaScript. I said Emscripten before. What I should have said was assembly JavaScript is a highly optimized performant subset of JavaScript. So this is not a new version of JavaScript. This is a subset of the language. So it's largely led by Mozilla and started as a research project by Alon Zakai and his partner in crime, Luke Wagner, perhaps the two most proficient names behind this technology. But the principal benefit over ASM as a whole over other technologies, like Pinnacle, which I mentioned before, is that it works today. So existing JavaScript engines already optimize this style of code very well. And I'll highlight in a later slide browser adoption. So the plan is to keep optimizing JIT or just-in-time compilers, but JIT compilers have less predictable performance based on complicated heuristics. So the asm.js model provides a model closer to that of something like C or C++ by eliminating dynamic type guards, boxed values, which are data structures that are minimal wrappers around primitive types. And box values are typically stored as pointers to objects on the heap, which we all know is not very efficient or fast way of getting information. And finally, garbage collection. So we can get rid of that by using something like asm.js. So here's an overview of roughly how it works. So I highlight C# here because later on I'll be showing you exactly how a middleware tool such as Unity can take your C# code and actually spit out JavaScript. But generally, someone would take something like C or C++ code and run it through LLVM. Again, that's that low-level virtual machine, which is going to be used as our Clang, our front end. Then we're going to run it through LLVM and Emscripten, and it's going to spit out JavaScript on the other side. So again, a huge benefit of this is we can take some of these legacy applications that were previously made for desktop devices or even mobile devices and have it working inside of the browser. And at very, very good speed because of this highly optimized subset of JavaScript. So again, Emscripten is an LLVM-based project that compiles this C and C++ code into highly performant asm. So near native speeds using C and C++ inside the browser. Even better, it can convert things like OpenGL, a desktop graphics API, into WebGL, which is the web variant of that API. So if you're familiar with something like Babylon.js or perhaps Pixie.js, you have seen some high-performant WebGL or graphics code inside the browser. It's open source under the MIT license and began in 2010. So Emscripten is built on LLVM. So that's great for a number of reasons. The first is that we have the Clang C++ front end, we have the LLVM optimizer, and then we have a bunch of library support as well. So things like libc++, which is a C++ standard library. So that means a lot of the C++ functionality or functions that we'd like to be able to call, we can actually do through JavaScript. Because we can make these calls in C++ and it'll actually be spit out in JavaScript and work perfectly fine. libc, which is a low-level C++ support library, works as well. So Clang supports nearly all C++ features, and again, Clang was that Apple-based compiler, so Emscripten does as well. Exception handling does take some work, though. So right now, I'm going to show you exactly how exceptions are implemented in C++, and then also how something like Emscripten will handle it in JavaScript. So right here, very simple use case. We have some C++ code where I have a simple try catch, right? We're going to have a function that'll try something. You put the name of your function in there, and then catch, and we're going to have a handler for that type of error. In JavaScript, a little bit more work, right? So we have a void function. And this void operator essentially allows us for inserting expressions that produce side effects in places where expression that evaluates to undefined is desired. So the void operator is used merely to obtain the unidentified primitive value. In this case, the global variable undefined can be used instead. So what we're going to try to do here is we're going to invoke a value of 10, which is going to be a call to a function pointer. So we're going to check for throw, and I'll show you what these functions are in the next slide. And if we can handle this type or this ID, we're going to have a handler for it. Otherwise, we're going to throw an exception. So here's a couple of those functions that were used just before. I have invoke, which is going to throw an error. We're actually going to try to make a call to the pointer. And then if I can handle it, right, we're going to call into one of those low-level C++ libraries that I'd mentioned before that Clang had offered to us. And if not, I can just throw an error. So what about other libraries, right? I mentioned there were some of those low-level C++ libraries, but what about ones that I want to use every day? Things like physics or graphics or scripting. Perfectly fine, it's available. So things like SDL, so that's a simple direct media layer, and OpenGL are also implemented via web APIs, and the same with Muscle, which is a Linux API. So things like bullet physics, box 2D physics, other things like Python or Lua for scripting, Ruby, zlib for texture compression. Those are all C and C++ libraries that are made available to you in the browser with JavaScript. Sounds fantastic, right? But with all these good things, there are definitely some limitations, let's be clear. And this is not without its limitations. So for example, 64-bit integer math just will not work. There's no multi-threading with shared state. So if you're writing applications that relies on more than one thread, it's not going to work in this case. JavaScript is a single threaded language, so everything works and operates on the UI thread. We do have things such as web workers, which will allow us to spin up or at least simulate multiple threads using an external JavaScript file that we can reference. So essentially we could have this other JavaScript file known as a worker that could run off, perform some kind of task, and then message our application when it's finished. The problem is the pipeline from Emscripten to this browser technology isn't quite there yet, and the worker is not really supported in every browser just yet. And finally, I mentioned OpenGL and WebGL before. So Direct3D, Microsoft's 3D graphics API, largely supported by the DirectX platform, is not supported. So it's only for OpenGL at this point. So 3 somewhat large limitations there, but we have workarounds for a lot of this. The other thing is debugging, right? So this is a problem in general with compiling for the web. So source maps can help a bit, but browsers do have a lot more to do in terms of making debugging compiled code a smoother experience. So your best bet with this is probably to start with your compiled code first. So take a look at that, make sure that's all working 100% in your other language, such as C or C++, and then when it goes over to the browser, you can start troubleshooting and debugging it from there. So how does this all work? Well, there's no forced mind trick over here. I'm actually going to show you the different types that are available to you and how Emscripten actually handles them. So numeric types. In LLVM, we have int8s, 16-bit integers, 32-bit integers, floating point numbers, double precision floating point numbers. In JavaScript, though, we have simply the double, right? So we build for a 32-bit target because 64-bit integers cannot fit all the doubles. And in terms of performance, right, you're thinking, okay, my application absolutely flies in C or C++, but the browser, like I said before, previously it was known for being, nice to say somewhat slow, but it's definitely seen a huge improvement in recent years, right? So in LLVM, types and operations map roughly one-to-one to the CPU cycles. And RAII offers predictability. So resource acquisition initialization is a programming idiom used for several object-oriented languages, most prominently, though, C++, where it originated. So what it does is it holds a resource that is tied to an object lifetime. And it's done during object creation. And so that's when I have a constructor function that's going to create my object. And also object deallocation, so releasing or destroying this object is done during destruction by its destructor. If objects are created and destroyed properly, resource leaks do not occur. So we have a lot of this performance benefit that's giving in C and C++, where we have constructors and destructors to help us manage our memory. But in JavaScript, we don't really have anything like that. So in JavaScript, right, we have to run the virtual machine or the VM. We have just-in-time or JIT compilers with type profiling. And we also have garbage collection, which some people say is a gift and a curse, right? Often easier to understand how to learn how to program with a garbage collector because I don't have to worry about having to free up memory all of the time. Obviously, we have things like smart pointers, which can handle a lot of this for us a bit better in C and C++, or C++, I should say. But still, it's going to be a bit of overhead. We have to use something like a garbage collector. Even worse, we can't try to coerce the garbage collector in something like JavaScript either, right? It's just going to happen, and we may see a performance spike as the garbage collector starts to call and take back all these resources which we haven't cleaned up in the past. So builds. So for C++, we need to recompile for each CPU or each operating system, right? So OS X, I have to have a build there. For Windows, you need to have a build there. And then is it an x86 version, 64-bit version, right? For something like JavaScript, you have one build to rule them all, right? I just have a single index.html or JavaScript file, and that's going to run across all of these different browsers, as hoping that the browser vendors are supporting JavaScript and HTML5 correctly. But I don't have to build different versions of my website for OS X or for Linux or for Windows variant, right? I can just say, here is a website, go to it on your device. There's a lot to be said about that. So variables, LLVM, local variables have functional scope. And if you're a web developer, this sounds very familiar because local variables also have functional scope. I know, tell me more, right? Because now I'm starting to pique your interest, and hopefully if you're a web developer, you're saying, okay, there are some similarities here, I like it, but still there are definitely some security concerns, right? So JavaScript, we run in a sandbox environment, so we cannot see the machine it's running on, and that's for a good reason, right? We don't want someone to take some malicious code that's written in JavaScript and very easily penetrate your system and just take advantage of all the resources that are available to you there. So there will be a bit of an overhead running JavaScript code because it's got to run inside that sandbox environment. So C++, apps can use the system libraries, right? But applications must ship their own system libraries. Emscripten can fake a file system, kind of make porting easy because JavaScript doesn't really have one, or at least the browser. So it's interesting the way that they kind of handle some of this. And I have a tutorial on my website on how they do this too. So if you look at my name, Dave Voiles plus Emscripten, you'll see how I go through some of these tutorials, many of which I've gone through from the Emscripten website. And again, access to the local file system, which I briefly touched on before. So security concerns continued. Can be beneficial though, right? So the JavaScript stack is managed and unobservable or unmodifiable by executing code. So it's not necessarily a bad thing, right? So it can help protect the system and what's happening behind the scenes. And compiled C++ is immune to some types of buffer overflow attacks, right? That's another huge benefit to C++ too. So speed. All right, let's take a look at this. So loads and LLVM intermediate representation become reads from typed arrays, and that's binary data inside the browser, or at least for JavaScript, which can become reads in machine code. So here I have a very straightforward example where I'm showing you how typed arrays pretty much work like normal arrays, but I'm defining what the exact type is. So in this case, we have 64-bit floating numbers in an array, so it's the length of 8 items. And you can see the first item here is a value of 10, the second item here is a value of 20, and the third item here is the sum of those two numbers. So JavaScript typed arrays are array-like objects and provide a mechanism for accessing raw binary data. A typed array is a slab of memory with a typed view into it, like I illustrated right there, and it works very similar to how arrays work in C. So because a typed array is backed by raw memory, the JavaScript engine can actually pass the memory directly to native libraries without having to painstakingly convert the data to its native representation. As a result, typed arrays perform a lot better than JavaScript arrays for passing data for things like WebGL and other APIs that have to deal with this binary data. So typed arrays, array views act like single typed arrays to a segment of an array buffer. So there are views for all the usual numeric types with self-descripted names like a float32 array, float64 array, which I highlight here, int32 array, and an unsigned integer 8 array. So why would anybody want to do this with their code, right? So there's a number of reasons. First of which is to circumvent the app stores, right? You want to push updates, just update your web app. So now we can have people go to our website, and we can even wrap these websites as, we'll say, hybrid applications, which I'll discuss in another talk, using tools such as Manifold.js. And there's a huge benefit here. So we're not trying to do anything malicious or anything tricky, but the idea now is that we don't have to wait, for example, 1 week waiting period if I'm going to push an application to a store such as the iOS or Apple App Store. So I'll give you a practical use case. You go to push an application to the App Store, all right? It takes about a week to get it approved, get it through, then have it seen on the store. Works great. All of a sudden you push an update, you wait another week, that update goes live, and you have a bug in there, okay? Now all of a sudden everyone's playing with your application, but the people on there are suddenly reviewing you very, very low. They're saying, 1 star, 1 star, 1 star, does not work, crashes at launch, or crashes when it gets to this part. You and your developers come back and you say, oh, we realized what the issue is. We had one line of code that was wrong right here. Let's fix it. You fix that line, and then you go to update the app again, and you have to wait another week before it can get back to that store. Not very convenient, because the entire time that you're waiting, your application is getting downvoted into oblivion where people will never see your app again. Not a very good experience, right? We have something like a web application. The moment I make that change, I can push to something like get, and I can have version control there, and I can have perhaps my web host look at my get account. That's what I use pretty often for my Azure applications, specifically the games. I'll open source and store them on GitHub, and then I'll have my Azure website look at my GitHub repository, so that this way, as soon as I push code to get, the website looks at it, grabs those changes, and updates the website. So now you can get changes seconds after I push them. And as soon as the user goes to refresh their page on the application, you have the updates there. Great, right? So download just parts of the app and stream the rest. So let's look at something like Star Citizen, right? Highly anticipated game from Chris Roberts coming out. He's of Wing Commander fame. So if you grew up in the 90s liking space operas and space shooters, he was one of the lead developers behind those kinds of projects. So the new game that he's working on now, Star Citizen, is going to be over 100 gigabytes in terms of size. So sure, you might say, oh, that's the edge case, right? 100 gigabytes. Fine. It's like something like a Blu-ray disc, right? Many of us have modern consoles, so PlayStation 4, Xbox One. Many of those games are 40 plus gigabytes in size, and then patches can often be gigabytes to download as well. So we'll say 50 gigabytes, all right? We'll be modest here. So 50 gigabytes for some of these titles. That is absolutely massive for someone to have to install 50 gigabytes because they may not even see that end of the game, that last boss I talked about earlier. So why should I have to download this entire thing, right? Or something like Age of Ascent, which is a WebGL spaced shooter. You can look this up online, and they have a fantastic story about how they're building this WebGL game for online shooting, or at least for space sim. And they go over how they built a lot of technology around this. So I have them on an interview in my podcast as well. So you can go to indiedevpodcast.com, and you can find out exactly how they're building this. What they do is essentially just start you with a very thin client that you can get within your browser. And what this will do is it only download the immediate parts that you need to get going. So in seconds, you'll have this space opera going. We're commanding the ship. And then as you get further and further in the game, you can start to stream that content to you, all right? So you don't need it all right away, but later on it can come to you. So I know what you're saying, but 50 megabytes for a website? Well, this is absurd. Who would ever want to download a 50 meg website? And you're right, if you're looking at it as purely a website, yeah, that is large, but we do have technologies that can cache and store a lot of this data within your browser, and I'll cover those a little bit later. And again, 50 megabytes, huge for a website, but I bet you're watching Netflix or Amazon or Hulu or YouTube, right? Every time you go on there, you're downloading hundreds of megabytes, if not gigabytes of data. So it's the exact same thing, right? Would you look at that YouTube video you watched last night for an hour and think, oh, man, a website, I would never go to a website that takes more than 100 megabytes. Well, what do you think you just watched? House of Cards comes out and people binge through that, right? A lot of people are watching in 4K now. So at 4K, right, that is a massive, massive chunk of video, but you're still looking at it as a website, right? You're getting it through your browser. So I'll cover this in a little bit more detail later on, but Jonas from the middleware development tool Unity can actually talk about how streaming some of these assets is already possible using something called asset bundles in Unity, which I'll cover a little bit later too. And again, distribution through sources other than curated stores. So again, we look at things like Steam, fantastic way for getting your game on PC, but often you have to go through the green light process, which can take weeks, if not months. or you have to go to something like the iOS or Android store, which we know is very difficult to get in front of all those eyes there. But what if we could do that and then also release our app on our website, right? Maybe even cut out the middleman. So now we don't have to pay 30% of our profits to them. We could perhaps guide them back to our own site and say, hey, if you want to buy this content, you can get it from our site right now for perhaps less money or the same price, then you would take a larger part of the cut. Not bad. So browser support, what does it look like right now? Well, I took the screenshot about a week ago, so this is early December of 2015. I mentioned what asm.js is. So I grabbed the screenshot from caniuse.com, which is a fantastic online resource for finding out which browsers are supporting which features on that current day. So this is updated pretty consistently. But what I want to highlight here is the fact that how asm.js is supported right now. So IE, right, Internet Explorer, we can see no support anywhere. I would not see it coming. As you saw, we are starting to deprecate support for IE starting, I believe, January of 2016. So Edge is our new evergreen browser where Microsoft will be pushing updates on a consistent basis. And to see in the latest version of Edge, which is available to you today, asm.js will play just fine. In fact, we've had several blog posts about exactly this. Firefox obviously supports it very, very well. They were one of the first developer to push this. And the first time I'd seen something like this, they'd actually showcased it with Epic Games at GDC, the Game Developer Conference, about 3 years ago. And I sat in for the talk thinking, I'm going to see what Mozilla is doing for video games right now. Sure enough, Epic came on stage and said, hey, we're going to show off our engine, the Unreal Engine, playing inside the browser. And I was blown away the first time I saw it. And since then, I've just been enamored by all this technology these companies are working on. So Chrome is yellow, as you can see here. And the yellow means that not all of the features supported just yet, but still many of them are. I'm not sure what exactly is missing in this case. Safari, still no support yet. The Opera browser, bit of support. And on mobile, there's not much going on here yet. So I wouldn't be too concerned with mobile platforms. Sure, you're missing out on a big piece here, but you're going to have a difficult time taking a lot of this legacy code and bringing it over to mobile devices just yet. So I might hang tight for a little bit before I'd consider getting to those platforms. So what does this look like? I'm going to show you a native executable. This is how I would write some of this code if I was going to do it in C++. And I'm going to show you the same thing, or the same bit of code, and how to get it running with Emscripten to get it working in the browser. So right here, I have a very simple hello C++ file. So I'm going to include the IO stream, right? So I can have my standard output here. So I'm going to say hello world, right? The opening application for just about everybody. So in the bottom there, that's where I'm going to use GCC. And I'm going to say point at this hello world file and output it. And this is exactly what it does, right? It runs that main application and it just says hello world, right, as a string. Very straightforward. So now that same C++ code, I'm going to leave that alone. And all I'm going to change is the compiler that I'm using. So instead of that, I'm going to use EMCC, which is the Emscripten compiler. So I'm going to say, look at that hello world file, and using Node.js, I'm going to output that HTML file. Very straightforward. Here are the results. This is me using Edge as part of my tutorial around October of this year. And you can see we have hello world running inside a little container inside of my browser. Not bad at all, right? So short, very, very simple use case, very simple example. Again, if you go to the Emscripten site, as well as my blog at daveoils.com, they have many, many more examples of how this works. I just want to show you a very simple file and get it running through the browser. That's all I want to highlight here. So generating some of this code. So the target file name extension defines the output type to be generated. So in that case, let's go take a step back. All right, I said I want to output HTML. So this HTML will also have a JavaScript file with it if necessary. So I could say let's output this file as JavaScript or JS. It's going to be JavaScript, HTML, and a separate JavaScript file, which is what I did just before. And having the separate JavaScript file actually improves page load time. And finally, I could use .bc, which is the LLVM bitcode, which is the default output that's going to be there. So EMCC is a drop-in replacement for your current compiler, whether it's GCC or Clang. And in many cases, you can just use your normal build system, plug in EMCC, and you're just ready to go. Not bad, right? So connecting C and C++ and JavaScript, right? You have all these function calls you want to be able to make. How do you do this? Well, if you want to talk to your system, you can use call compiled C functions from normal JavaScript using a number of options here. Soccall or crap. I can also call compiled C++ classes from JavaScript using bindings created with mbind or WebIDL. And then I can call JavaScript functions from C++, so I can go the other way around. I'm using a number of tools here. So Emscripten has quite a few included, such as runscript or Emscripten asm, which can be a bit faster. So I'll let you dive into these a bit on your own, as we just won't have time for it here. So you're probably asking, why not just turn your JavaScript code into assembly JavaScript, right? Well, there are a number of reasons. So JavaScript can't be compiled to asm and offer much of the benefit because of its dynamic nature, right? So it's the same problem when you're trying to compile it to C or even native code. You need a VM for it to be necessary to take care of those non-static aspects that are available to those languages. So another thing is that runtime checking takes time, right? So to better understand this, it's important to comprehend why asm.js offers performance benefit at all, or why statically typed languages perform better than dynamic ones pretty often. One reason is, again, runtime checking takes time, and a more thought-out answer would include the enhanced feasibility of optimizing statically typed code. So a final perk of going from statically typed language, such as C, is the fact that the compiler knows the type of each object when it's being compiled. All right? So beforehand, as soon as we're building or compiling this project, it's going to know the type of all of these values. For JavaScript running inside of the web, it has to infer and then understand at runtime when we actually get to that line of code and go to execute it. Right? So a bit of a difference there. So an offline experience, right? We can take a lot of this code and we don't have to download it every time, right? We can cache it or save it in a number of ways. I just did this with an HTML5 video game project of mine where I was porting this classic game from the Sega CD called Night Trap, which came out in 1992. It was written in 68K assembly, and I ported it to HTML5 and JavaScript, and it's got tons and tons of video content. So I wanted a way to store a lot of this content inside the browser locally, so that every time someone went to go play this game, they didn't have to re-download all the content and all the video files. That, again, would be very stressful for their machine. Perhaps people are on limited bandwidth or they can't use up all their mobile data. That's fine. I don't want to be serving this content consistently too, because it's going to be taxing my servers and my machines. I'm going to get billed for it. So why not store some of the data that's not going to change? And we can do this. First would be app cache, which is what I wound up using. So it's offline browsing, and it stores content on the disk for your local device instead of a network. So you can use something called the app cache manifest, which is a simple XML file, which defines which assets you want to store locally. So that can be anything from HTML, JavaScript, MP4, images, or even video files. I've done it for all of this. And I'll have a tutorial which will follow shortly after. IndexedDB is another. So it's a local database of records holding simple values and hierarchical objects. So it might be wise to have a mix of local and remote content for your app. So technologies, again, such as IndexedDB and App Cache will help out, and they're even all supported in Edge. So a local page can be kept in your app package and can still provide basic offline experience. And finally, something like service workers are a useful option for offline caching too. So Matt Gaunt, G-A-U-N-T, has a fantastic article on service workers. So if you type in his name, Matt Gaunt, service workers, he'll give you a very good explanation of how it all works. But I'm not quite sold on this just yet. Not much in terms of browser adoption quite yet. But if I try to use something like app cache inside of Firefox, I actually throw a little warning and say, hey, this works fine now, but understand we will deprecate this soon in favor of service workers. I'm ready to make that switch as soon as it's available to more browsers as well. So performance. This is great, right, that I can take all this legacy code and have all these workarounds, but if it doesn't perform well, you're wasting your time. That's what I want to highlight right here. So this is from Unity, and I'll explain in a few more slides why I'm using Unity more than anything else here, but this is the Unity benchmark. Unity, again, is a middleware tool from Unity Technologies, which allows you to write code in C# to make high-performance applications or games. And generally, it's going to spit out a native executable that'll run for each platform, but what it can also do is actually spit out WebGL now. So let's look at these performance benchmarks. This is from the Microsoft Edge blog, where we had a post earlier this year educating users about how we're supporting ASM and the kind of performance we're getting. So these are a number of tests that we're running across the board here, everything from the Mandelbrot images that we're running on the CPU, and we're also running this on the script, or sorry, I should say the GPU and the script. So see on the far left-hand side there, we see Mandelbrot GPU. All those performance numbers are just about even across the board. And right now we're just testing Microsoft browsers in this slide. This is Microsoft Edge with ASM available in green, Microsoft Edge without ASM, so it's just our normal Chakra JavaScript engine running. It will be in orange or yellow, and IE11 will be in gray. So you notice on the far left there, when we're trying to do a Mandelbrot across the board GPU, or at least inside the browser, applications that rely on the GPU are going to be nearly identical across the board. When we go over to something like the Mandelbrot script, we can see there's a huge benefit in using ASM here, right? It's nearly twofold for whatever reason from what we have in Edge. Also, go over a bit more, we see particles. So IE11 just completely struggling here for whatever reason. And I don't want you to think that Edge and ASM are the same at this point for particles. I think it's just really there to showcase that they're both off the charts for whatever reason. But what I really want you to focus on is on the right-hand side there, you can see score. So this is your overall score for this. And again, higher is better. So it's taking the average of all of these tests, and we can see that Edge had a very good result. So at least Edge with ASM. So it's nearly double the performance of what we get with just typical JavaScript running inside of the Edge browser. So very nice use case there. Now, Unity WebGL benchmark you can get to from the Unity site. So you can just type in Unity WebGL benchmark, and it'll run you through a number of these tests. Now, Unity as a whole, they've actually wrote a blog post on this about a year ago. And when I was putting this together, I took several days to write this talk. I had a bunch of old information, or from the last test, and halfway through my write of this PowerPoint deck, they actually updated the whole thing, so I had to start to redo this. So here are their latest numbers from early December of 2015, where Unity is testing this on a Windows 10 machine using a 3.3 gigahertz i7 CPU and an NVIDIA GTX 960. So very similar to the machine I'm running here. I'm running this Windows 10. 3.5 gigahertz CPU and GTX 970. So I'd imagine I get very similar results. So see Firefox in the lead here with their 64-bit OS, which they had just released actually to the consumers last week. So before this, Firefox was running inside on your device, at least on Windows, was running 32-bit. It's now 64. And you see Firefox obviously has a bit of a lead here. And then Edge with asm.js enabled, coming in third very nicely. And then go down to the 32-bit version of Firefox, and it slows down a bit, right? So this is where you can really start to see a difference between 64-bit and 32-bit performance. And finally at the bottom there, we have Internet Explorer, which is just not optimized to be running any of this at this point. So here is what Unity has learned from this. So what they had to say was, in benchmarks which stress WebGL rendering performance, again, that's the web graphics library that's taking OpenGL and converting it to WebGL, such as particles, asteroid field, Edge performs the best of all the tested browsers. When you are mostly GPU bound, that is, you're using the graphics processing unit instead of the CPU, you can expect WebGL to perform very similar to native code. That's great, right? That is something we can really take home here, is the fact that code written for the graphics card is going to work nearly identical across the board, whether it's a native application or running inside the browser. It's the CPU where we're going to start to see some of these issues. So in some areas, WebGL will actually outperform native code significantly, and we saw this in the 2 slides ago, and this was Mandelbrot and CryptoHash. And this is for cases in which tests rely on a lot of script performance, as both of those scripts, their algorithms were implemented in C#. And finally, native code can still be several times faster than WebGL for areas heavily optimized for multi-threading and or SIMD, which is single instructions, multiple data, such as the 3D physics test. So again, SIMD not supported by every browser just yet. And like I mentioned earlier, we don't have multi-threading available to JavaScript. So with some of the Unity WebGL benchmarks out of the way, let's take a look at a case study. So Owlchemy Labs, a developer from the Boston area, created a game called For the Awesome, where essentially you are a character who's kind of skydiving through this debris and wreckage and falling through it and having to manipulate your character as you avoid these obstacles. So it was created in Unity, but they decided to be one of the first developers, if not the first, to port it to WebGL and did a great job of showcasing their experience. In fact, they put together a post-mortem on Gamma Sutra, which is a game development blog. And using the pre-alpha version of the WebGL exporter in June of 2014, they were able to take all of their C# code and turn it into one JavaScript file, which had more than 1 million lines of JavaScript. So in total, there were more than 200 levels and at least 300 assets, which could all be spawned at runtime. There are 38 full-length audio tracks or songs, more than 1 million lines of JavaScript, which is absolutely insane to imagine running inside the browser. And in terms of actual file size, their WebGL build with all of the Unity engine, which was necessary to compile and run this application inside of the browser, came out to 68.8 megabytes. But the PC build, so as the executable they then put into Steam and other stores, was more than 3 times the size at 192 megabytes. So kind of wild to think about how different this project turned out to be when they're porting it from one platform to another. So again, if you want to get a deeper understanding of how a lot of this works, I would really implore you to take a look at the Owlchemy Labs case study. So they posted on Gamma Sutra, I believe on their blog, and also on the Firefox blog to illustrate how well this worked inside of Firefox, as it was one of the first again, samples to port to WebGL using Unity. But again, WebGL is not limited to just Unity. What I want to show you here is, it's not just for games. Here is the Unreal Engine, which is not only, again, for gaming, game development, but applications as a whole. So before I got into programming, I was actually doing high-end commercial and residential real estate development in Manhattan. So we'd build very, very large and nice places for multimillionaires. And it could be difficult at times to have to pitch the idea to someone or help them visualize what their apartment or their building or storefront will look like with just, even 3D CAD drawings, which they can't maneuver their way through, or static 2D images or blueprints. So I always like to think back how I was doing that several years ago and think, what if there was a tool that had photorealistic 3D models that I could actually navigate through? And well, this tool is exactly that. So let's see how some developers have taken some architectural drawings, turned them into levels in the Unreal Engine, and again, all of this can be exported to the web through their WebGL and asm pipeline. Here we go. So now we have beautiful, high-resolution textures with real-time lighting and shadows inside of the Unreal Engine. So all this code is written in C++, but they do have something called blueprints for a sort of visual scripting for events that happen here. But you can write all of your own shaders as well. And this, I believe, is the executable version, but there's no reason you could not export this to asm and WebGL as well. In fact, they have a very good tutorial and a nice pipeline for doing exactly this. Now you can see somebody maneuvering the camera in real time, doing things like changing floor color, which simply swaps out the textures or the materials that are applied to some of these 3D models. And all this, again, is happening in real time. So I like to look back and think about how easy it would be to share something like this with the client and say, oh, you want to help visualize or understand what a difference would be? Well, what if I gave you the opportunity to quickly and easily swap out some of these textures, turn this to a mobile application or a simple app they can get on their tablet or even desktop machine, send it to them as a link, even through Twitter or email, and then all of a sudden they instantly have that application that can make these changes on the fly. Again, without having to download an entire massive project and install it and hope that it works on an operating system. So you get the gist, but again, I implore you to look online and see several more of these. So again, that was for the Unreal Engine by Epic Games. For Unity, their pipeline is very straightforward. This is an older photo. You can see that WebGL is still in preview, and now it's part of their final build as of Unity 5.3, I believe. You have several optimization levels here. You can see optimization level low or slow creates a fast build, and that just gets it out the door immediately. So it's not really going to optimize performance. You just want to get this out so you can try out this project. So the user would hit build and run. It would then spit out a project for you. But here's exactly what it spits out. What goes in must come out, right? So if you're going to build a WebGL project with Unity, it's going to create a folder with the following files. Right? Every web page has a main entry point, and that's generally index.html. So this embeds the content of your web page. You then have a JavaScript file containing the code for your player. Now your player is actually what Unity runs inside of. So whether you're running a web project or a game as an executable on something like a desktop platform, you're always going to have a Unity player included. The .mem file containing a binary image to initialize the heap and memory for your player, the data file containing the assets for the data and the scenes, and finally, you're going to have some supporting JavaScript files to initialize and load the player as a whole. But of course, there are some missing features. So like I said before, there still is not a one-to-one mapping in terms of every feature for a compiled or executable project, I should say, and a web project. So networking, other than the www classes that are included with Unity, are not there, but a WebSockets plugin is available. Support for the webcam and microphone access, still not there either. Like I mentioned before, JavaScript is single-threaded, therefore we do not have a threads workaround at this moment. Any .NET features requiring dynamic code generation, they're not there. And finally, runtime generation of substance textures. So substance textures you can think of are textures that have physics applied to them. So if I was going to add perhaps rubber to a ball and then bounce it on a wood floor, that ball would behave differently if it was hitting a hard floor than if it was perhaps a floor that had a soft texture applied to it, like a carpet and whatnot. So coming around the home stretch, the advantages of porting a C or C++ application to JavaScript are very clear, hopefully, after this. They include often a smaller package size. You can easily demo or share your projects on the web. Again, I can have a website, and I can just point someone towards that through Twitter, email, anything of that nature. And finally, you have the opportunity to reuse a lot of your existing code, right? You may not even have to rewrite all of this, whether it's a legacy application or something you wrote in another tool. Instead, give it a try through Emscripten and see how it works out through there. Brandon Ike, again, like I mentioned before, one of the creators of JavaScript, if not the sole creator, has a great website that he points people towards, and I wanted to use this to wrap things up. And that is Always Bet on JavaScript. And right here we have Wesley Snipes from Passenger 57. First, they said JavaScript couldn't be useful for building rich internet apps, right? But you see that we have plenty of rich internet apps right now. Then they said it couldn't be fast, and I think through some of the benchmarks today, I should have you convinced that JavaScript is a very, very fast language today. They said it couldn't be fixed. I mean, sure, it still has its issues, I can't deny that, right? But with ECMAScript 6 or JavaScript 2015, whichever you prefer to call it, I think we got a lot of those changes in there now, and it should be more comfortable to people coming from classical languages like C or C++, and then we have classes and modules and things of that nature. They also said it could do multi-core GPU, but I showed you right there, right, using something like WebGL, which is taking OpenGL content and running it on the web, works perfectly fine, and these people were wrong every single time. So Brandon Eich's advice, and mine as well, is always bet on JavaScript. Finally, I want to point out some references. So Alon Zakai, @Kripman on Twitter, has been the mastermind behind this project. So it is his research that led to all of this. He's been putting this together, got hired at Mozilla, and is then on the research team to help build this, along with several other people, like Luke Wagner comes to mind. So most, if a very large portion of this content that I got came from what I was able to piece together from several of his talks on YouTube, many of his slides and talks that he's given that I've seen at perhaps the Game Developer Conference, and also from browsing his website. So if you want to learn more, I encourage you to follow him, take a look at his work, and check out his GitHub repository where he has quite a bit of information on how all of this works. So I'm very excited to see how Emscripten continues to take off in the future, as well as asm.js. And if there's anything that I can do to help, feel free to reach out. Again, my name is David Voiles, and I'm a technical evangelist at Microsoft. You can find me at Dave Voiles on Twitter, or on my website, davevoiles.com. Thank you.